Hello, this is part A of Calculus Variations, General Theory. Parts A and B of General Theory are going to introduce general concepts in functional minimization and optimization. I will talk about issues to do with existence of minima. I'll talk about a great many things, but they won't be done in a setting where we can derive Euler-Lagrange equations quite yet. It merely provides the background so that we can derive Euler-Lagrange equations later to solve problems. So let's start. This talk is relatively short. I'm going to give you examples of functionals and their associated minimization problems. Then I'm going to talk about existence and uniqueness considerations, and I'm going to do this via examples. Lastly, I'm merely going to introduce the concept of continuous functionals. So functionals are a little more general than functions, but you can still talk about their continuity. Anything to do with differentiability, which has to do with optimizing, is going to be on part B of this series. Let's recall what a functional is. If you're given some set, A, called the admissible set, a functional on A is simply just a map from A into the real numbers. So I think before I talked about the possibility of A could be the set of red shoes and red and black shoes, and if they're one color, you get a value 1. If they're another color, you get a value 0. That's actually a functional. But when what we're going to be doing is we're going to be picking very special admissible sets that are relevant to different problems. And typically our admissible set themselves will be sets of functions. So J is a function that maps from a set of functions into the real numbers. Our basic goal is down here is we want to find the minimum value of J of Y, or possibly the maximum value. And I'm only going to put in certain Y's, and the Y's that I'm going to put in are the ones that are admissible, i.e. define the set A, do the minimization over that set. So if there is a minimizer, and we're going to say I'm going to use bar to indicate when I talk about minimizers themselves. So what is that? A minimizer would be an element of A typically that may not be an element of A, but it could be. It's typically an element of A that when you put it into J, it spits out the minimum value. That's like saying the minima of a function f of x is attained by some value in the interval. So we'll just define, this is notation that's given in other textbooks, argmin is the set of minimizers. Namely, so it's the set of y's that when I evaluate j at those y's, I get the minimum value in the problem. It's important to recall that whenever I'm talking about functionals here over admissible sets, I could just as easily have been talking about functions of on a subset of Rn mapping into R. And those are the standard calculus minimization problems you see in first and second year calculus. But we're going to do, our set A is a little more general. And but just remember that at any point in all of this, J could be f of x on Rn, and the admissible set could be some set of Rn, maybe a sphere or something like that. Okay, some examples. Point evaluation functional. Point evaluation functional. What does this do? Okay, define the admissible set. The admissible set here, I'm going to define to be CV02. That means the set of continuous functions on the closed interval 0, 2. The value of j on that set will be defined to be the value of the function at x equal to 1. So what this function does is it takes functions y and it evaluates those functions y at x equal to 1. That's the point evaluation functional. This functional has no minima because I can pick y's that have arbitrarily small values at x equal to 1. There's many, many continuous functions, and I can make them having smaller and smaller values at x equal to 1. Second example, area functional. Area functional, well, I need to be able to integrate the function, so I'm going to make my admissible set equal to y's that are continuous on 0, 1 and are strictly positive. That way, this definition for j, the integral, is some non-negative number. Is there a minimum of j of y for all possible functions y in this set A? The answer is yes. I could take the 0 function. Y of x identically equal to 0 everywhere is certainly continuous on 0, 1, and it's greater than or equal to 0 on 0, 1. When I integrate it, I get j of y is equal to 0, and that's the smallest area you can have. Next example, arc length. Think R3. So n could be 1, 2, 3, but I'm just going to do, I'm going to think of this number as being 3. Because then this is a parameterization. Y of t is a parameterization of the curve in R3 or Rn. And this is a set of basically all curves that are parameterized and equal to a point in space at one endpoint and a different point in space at the other endpoint. Namely, when t is 0, y is equal to a. When t is 1, y is equal to b. From calculus, we know that if you take the components of y, of which there's n of them, you differentiate them, square them, and add them all together. You do this square root and integrate, you get the arc length of that curve in space. So this is the arc length element. The minimum would be the straight line from A to B. If we were talking about, let's say, R3, for example. So that straight line would be have a minimum length. We'd actually have to prove that technically, but we know that to be true, so I'll just say it. Okay, so that's just another example. So here's one we saw in the previous introduction too. U's that are twice continuously differentiable on a subset omega of R2. So imagine omega here could say be a circle, the interior and boundary of a circle. So this U is the graph above, a relatively smooth graph above the circle. And the additional constraint is that on the boundary of that circle, that's this partial sign means boundary of the set omega, it's equal to some prescribed value g. So U is equal to some value on the boundary, but otherwise it can be wiggly and have some smooth shape. Its arc length is going to be given by the arc length formula from multivariate calculus, which is 1 plus the norm of the gradient squared. Does it have a minima? Typically, yes. You can get more abstract. I put one in here, which is practical, actually. If you have L is any self-adjoint operator on a Hilbert space, so you have this statement here. The dominant eigenvalue of L is given by the Rayleigh-Ritz quotient. If you've never seen that before, you can look that up. But basically it goes like this. That dominant eigenvalue will equal the minima of J of U if J of U is defined to be the operator acting on U, inner product U. So this quantity here will be real because L is self-adjoint. And then of all the u's that you can put in here, we're only going to consider the u's that have unit length. So of all those admissible u's, you put those into this formula, find out what the minima is, and that value will be equal to the dominant eigenvalue of the operator L. That's very abstract, but I'm included it here because J's can be a lot of things, A's can be a lot of things. Existence and uniqueness. Okay, so this is a typical kind of thing you get in calculus. We're going to do it in one slide for functionals. And it goes like, here in this example, we're going to, the functional j of y is going to be the derivative squared minus 1 absolute value, then integrate dt. Okay. It's pretty clear. So if I'm integrating the absolute value of anything, the smallest that j could become then would be 0. That would happen when this integrand is equal to 0. In other words, j of y can attain its infimum of 0 if y dot squared is equal to 1 almost everywhere. That's what this statement here says. All right. So that's just the prelude. Now let's consider minimizing this function over 3 different admissible sets, A1, A2, A3. A1 will be continuously differentiable functions on 0, 1. A2 will be continuously differentiable functions on C1 that are pegged to be equal to 0 at both the left and right endpoint. So it's a strict subset of the preceding one. A3 will be y's that are piecewise C1 on the interval. That means that I could get a finite collection of intervals of 0, 1 on which each of those intervals, the function is C1. But at a certain finite number of points, there might be a problem with differentiability. Something like absolute value of x doesn't have a derivative at x equals 0, but it would be a PC1 function on negative 1 to 1. So, smooth functions that vanish at both endpoints, pretty smooth functions which vanish at every endpoint. This minimizing j over a1 is easy because this integrand has to be continuous, and the only way that can happen is if the y is equal to plus or minus t. Because if y is equal to plus or minus t, the derivative is plus or minus 1. You square it, you get 1 minus 1 is 0, and the integral therefore is 0. So the minima of j of y is attained by 2 different y's in the admissible set A1. That's case 1. Case 2, how about A2? Well, there are no functions that are smooth equal to plus or minus t that also equal to 0 on both boundaries. It's true that this thing here equals to 0 on the left boundary, but it doesn't equal 0 on the right boundary. So what does that mean? That means if I try to minimize j over only these kinds of functions, the answer is there is no minima for those kinds of functions because of what I just stated. So minimize j over a1, you have 2 minimizers. Minimize j over a2, you have no minimizers. A3 is a little more interesting because you can construct these cute functions. It has an infinite number of minimizers. And we can see that. So PC1, so these are functions that have like a finite number of points where they're not C1. So I've color-coded 3 in black, blue, and red. The black one goes from 0 up to a height of 0.5 and then down to 0. And it does the peak at 0.5 by making that 0.5 with a height of 0.5 makes this slope 1 and the slope on the other side -1. So if I take this black function and I take the derivative of it, it will be plus or minus 1, except at one point where it doesn't have a derivative. Still, it's plus or minus 1 on this interval, plus or minus 1 on this interval, so the integral is 0. Let's make a second function in PC1. That's this blue one. At 0.25, it has a height of 0.25. Then it goes down. Then at 0.75, it has a height of 0.25, and then it goes down. The slope of this blue thing here is 1. The slope of the blue thing here is negative 1, plus 1, negative 1. I take its derivative, square it, and subtract 1, and I get 0 everywhere except at the 3 points where it doesn't have a derivative. Right there, right here, it doesn't have a derivative. Right there, it doesn't have a derivative. And right here, it doesn't have a derivative. So it still gives me j of y equal to 0. Same thing with, you just divide the intervals in half again and lower the height by a factor of 2, and you get a more cross-cut saw kind of shape like this. And I can get smaller ones embedded in here. And you create a sequence of these kinds of things that make this functional equal to 0 for these kinds of functions in A3. So what do we conclude? The minima of j of y over A3 is equal to 0, and it's attained by many, many functions, some of which are the ones I've drawn here. Here's one that maybe seems less contrived. It has to do with a polar arc length problem. Problem is this. I'm going to consider, so r of t, t here, think of that as being theta in a calc course. It's just a parameter. R of t describes the polar curve. And I'm going to have a polar curve where the curve starts at the origin and it ends at a distance of 1 at the angle t equal to 1 radian. The arc length formula for such curves, so these are the curves I'm talking about down here. That's the admissible set. Smooth curves that start at the origin and end at 1 at t equal to 1. This integrand here is determined, the integrand for j of r is determined by, in calculus, there's a derivation for that formula. And what you do is you take your r of t, you put it in here, square it, you take its derivative, you square it, and you take this sum, and that will give you the arc length of the curve. There's lots and lots of functions in this set A. I'm going to give you a very explicit set. Rn of t is equal to t to the n. That describes a kind of a spiral. But remember, our angles are only going to go from 0 to 1. Okay, so it's a spiral for n equal 1. For n equals 2, it's a slightly different spiral. For n equals 3, it's a different spiral. The arc length for any one of these is given by this integrand. I got that by simply putting this formula into the general formula above. And you can factor stuff out from the integral sign, and you get t to the n minus 1 times this square root. It is true that you can actually evaluate this thing, but it's a real mess to do it for an arbitrary n. So I'm going to do something else. I'm going to use a little bit of analysis. I'm going to find an upper bound for the value of the arc length of this class of curves. How I'm going to do the upper bound is I'm going to make this integrand bigger. So in particular, the part that I've got highlighted here in blue is smaller than the part I've got highlighted in blue on this side. Because if you expand that out, you've got an extra 2nt term in there. So that means this integral is bigger than or equal to this integral. Well, now that's the square root of a perfect square. So I merely have to do t plus n times this term and integrate it. So I can easily evaluate that. This integral turns out to then be this 1 plus 1 over n plus 1. That's just calculations. So what do we know? We know that if we take, you look at all this family of curves, these family of spirals, their arc lengths are all less than, they have an arc length less than or equal to 1 plus 1 over n plus 1. As n gets big, this thing approaches but never actually equals 1. What does that mean? Well, let's see what it looks like on a graph now, okay? On this graph, I've drawn Rn for n equal 1 and 2. So this one here is the spiral. R of t is equal to t. And it would continue on if you wanted to, but we're stopping at a distance from 1 from the origin. If t is 2, so r is equal to t squared, I get this curve here, which is a little shallower, but it hits the same endpoint. If I increase n and make it bigger and bigger, the curve gets flatter and flatter and flatter, and it approaches the straight line from the origin to that point. That straight line has a length of 1. What that means is that the length of each and every one of these things has got to be strictly bigger than 1. So any one of these things has any j evaluated at any r in A is going to be strictly bigger than 1. But here I've got a sequence of them that approaches 1. What does that mean? Okay, so you think about this. This says that this sequence approaches the infimum of j, but there's no actual element r in A that makes j 1, because j has to be strictly bigger than 1. Hence, there is no minimizer in this set A that minimizes j. There are functions that do minimize j, but they're not in this set A. That's all I'm saying. Okay, last thing is a brief introduction to continuity. So pretty much henceforth, when we're talking about continuity and later an analog of taking derivatives, we're going to be talking about sets that are in some normed linear space. All right, so so they've got a length, could be induced by an inner product, and typically V are spaces of functions. So I've got subsets of spaces of functions. And to say that J is continuous at a point in A is almost identical to the definition for continuity of functions f of x. That is to say, if I pick an epsilon greater than 0, and I look at how far away j of y is from j of y naught, it's small if the distance between y and y naught is sufficiently small. So here I'm using the norm to get the distance. Here's an example. Admissible set will be continuous functions on 0, 1. The functional is the functional that computes the integral. J of y is continuous on A with the infinity norm, I claim, since if delta equals y, the following is true. How do I prove this? I'm going to try to show that if I'm given an epsilon and I try to compute the blue thing, that's in the definition up here, this blue thing, I'm going to try to compute that. And the goal is to show that it's less than epsilon if the norm is less than delta equal to epsilon. So let's see how that happens. You start with this quantity, you write it out explicitly, and you get this formula. You get the integral of the difference of the functions. Okay, there's a theorem that says that if I take the absolute value of the integral, that's less than the integral of the absolute value. By taking absolute value under the integral, you can only make the integral bigger. So I do that. So I've got this quantity is less than or equal to the integral of the absolute value of these functions. Well, the biggest that this integral can be is the biggest that the integrand can be times the length of the interval of integration. Now, the length of integral of integration here is 1 minus 0, so that's 1. So the biggest that I can make this entire thing is the length of the interval times the maximum value of the integrand. So that is simply less than the maximum value of this difference on the interval. Well, that's nice, because this max of this difference is exactly what is meant by the infinity norm on the space of continuous functions. So again, if I pick an epsilon, this thing will be less than or equal to epsilon so long as the functions are close enough to each other, in the sense that this infinity norm, or this quantity here, is less than or equal to epsilon as